In this video, we're going to derive the state equations for this bond graph that's shown, and then we're going to place them in matrix vector form, x dot equals ax plus bu. So to begin with, we're going to write down all of the element equations, one for every element in the bond graph, plus 2 for every junction in the bond graph. We'll start at the effort source, E1 equals F of t. For our resistance, we have F3 equals E3 divided by R. For our capacitance, we have E2 equals Q2 over C2. For our inertance, we have F5 equals P5 divided by I5. For our other capacitance, we have E6 equals Q6 divided by C6. For our first one junction, we have F2 equals F3, F1 equals F3, and F4 equals F3, because F3 is the causal input flow variable, the independent flow variable to the one junction. And for the efforts, we have E3 equals E1 minus E2 minus E4, which comes from our balance of power. For the zero junction, we have E4 equals E6, E5 equals E6, and F6 equals F4 minus F5, which comes from our power balance. At this point, we need to identify what the inputs to the system are and what the state variables are. We'll start with the state variables. We see that we have 3 elements in integral causality, both capacitances and the inertance. So our state variables are Q2, Q6, and P5. And we have only one input, which is F of t. At this point, we're ready to start deriving our state equations. So we write down the basic state equation, Q2 dot equals F2. We're then just going to expand this F2 into F3. And we expand F3 by looking for the equation which has F3 on the left-hand side. We find E3 divided by R. Now we look for the equation with E3 on the left-hand side. We find E3 equals E1 minus E2 minus E4. We carry through. E1 is F of t. E2 is Q2 divided by C2, and E4 is E6. So we're not quite done yet. We need to expand for E6. And so we're going to find F of t minus Q2 over C2 minus Q6 over C6 all times 1 over R. So I'll just rewrite this by multiplying through by our 1 over R. Now we can move on to our second state equation for Q6. We know that we're done with Q2 dot because the right-hand side includes only parameter values, inputs, and state variables. So Q6 dot is F6. That's our basic state equation. It's the definition of Q6 dot, or F6. This is equal to F4 minus F5. F4 is equal to F3, and F5 is equal to P5 divided by I5. So F3 is equal to E3 divided by R, and we still have our minus P5 divided by I5 because that term is done being expanded. Now at this point, we can save ourselves some work by noticing that we already solved for E3 divided by R. It's equal to the right-hand side of Q2 dot, so we can short circuit the rest of our substitutions, copy the value of E3 divided by R that we found already, and then add in our last term, our minus P5 divided by I5. Our final state equation for P5 dot, this is equal to E5 by definition of the basic state equation. E5 is equal to E6 thanks to the zero junction, and that's equal to Q6 divided by C6 from our capacitance. So we're going to place this in matrix form as requested by the prompt. We have our time derivative of our state vector, and here we can choose any order that we like for the state variables. I'll just choose Q2, Q6, and P5 in that order. We look at our Q2 dot equation. The coefficient of Q2 is minus 1 over RC2, then the coefficient of Q6 is minus 1 over RC6, and our coefficient of P5 is 0. In the Q6 dot equation, our coefficient of Q2 is minus 1 over RC2. Our coefficient of Q6 is minus 1 over RC6. And our coefficient of P5 is minus 1 over I5. Finally, in our equation for P5 dot, we have only one term, and our coefficient of Q6 is 1 divided by C6. Our input matrix, we look for the coefficients of f of t in each equation. We find a 1 over r in the equations for Q2 dot and Q6 dot, but no coefficient of f for P5 dot.